It's a quadratic, so you should be able to know. It's just a parabola that's been shifted.
Shifted down 3 units.
Okay, tell me some things about how this parabola is behaving, how x squared minus 3 is behaving.
It's concave.
Okay, the end behavior is increasing forever to the left to the right. Okay. Think about it like if it was in like a physics problem, probably your independent variable would be what? What would x stand for? Time. So if I am talking about time, question, how do I have to talk about the progression of time? Can it go both directions, to the right and to the left?
No.
Time only goes one way. It only goes that way, right? Which is why we're going to be talking about graph behavior as only going from left to right. That sounds a lot like pre-cal, right? From left to right, is a graph decreasing or is a graph increasing when you learned interval notation last year? Okay, come back. So question, let me ask you again. Yes, the end behavior, it's like going to infinity to the right to the left, but how is it behaving? Decreasing from negative infinity to
Negative 0 and then 0.
to 0, because how do we talk about intervals where? X values. So it's going to be decreasing from negative infinity to 0, right? What else?
0 to positive.
Increasing from 0 to positive infinity. Is there anything else you can tell me about how this graph is behaving? It's going to have a minimum. It's going to have a minimum at 0, negative 3. That's true. It's going to be concave up everywhere from negative infinity to positive infinity. What did you guys tell me? There's a minimum at relative or absolute, or doesn't really matter? Both. Both. It's the very lowest, and it's also the lowest in its region. So minimum was at what? 0, negative 3. And then you said concave up from negative infinity to positive infinity. Anything else? How is his derivative behaving? It's a line. What do you mean? Because what is f prime? Let's go ahead and go to b. F prime of x is equal to 2x. Okay, so it's a line. How is f prime then behaving?
It's just increasing.
Why is it increasing? How can you tell on this graph that he is increasing? How can you tell the first derivative is increasing on f's graph? What does f prime stand? What's happening to the slopes as I go from left to right? How are they increasing? Can anybody visualize that and see, wait a minute, they're increasing? It's getting less steep, but hold on, it's getting less, what sign does it have right now?
Negative.
So if it's getting less negative, what is it getting? More positive, right? So even though it's negative, and it's really, and it's like, wait, it's flattening out. I know, but it's getting from more negative to less negative. Oh, it's going higher and higher and higher and higher. Now it finally gets to pass a 0 and go to positive, and so it's going higher and higher and higher. So my first derivative, I know I didn't have you guys graph it, but it was actually a really good idea to have you graph it. It would go strictly increasing. Interesting. What was your second derivative?
2.
So it would be, you're right, it'd be a horizontal line because we know each of the derivatives goes down a degree, right? So a squared to a linear to a constant. 2. Why is the second derivative staying constant? Well, what's the slopes of the first derivative? Positive, so it's a positive number, and it's positive 2, and it's staying always 2. Remember, the second derivative is just showing the behavior of the first derivative, and the first derivative is increasing at a constant rate. Wait, so derivatives are rates? Did we talk about that back in the very beginning of derivatives?
Yeah.
What are derivatives? Slopes of tangent lines, but also instantaneous rates of change. What's the first derivative showing the instantaneous rates of? The original. And what's the second derivative showing the instantaneous rates of? Nice. Okay, so you guys went ahead and plugged in stuff, right? And you got -4, -2, 0, 2, 4?
Yeah.
Okay, and then you got 2, 2, 2, 2, 2, 2, 2. I probably said way too many, but they're all 2s. True?
True.
Okay. What's going on with the sign change of derivatives from negative to 0 to positive? What's going on at 0 that makes my derivatives change signs?
It's going positive.
What's going positive?
The line.
The line is, but that's what the first derivative, remember, we're always trying to ask ourselves, hold on, what are the signs and or the sign changes of the first and second derivatives telling me about the behavior of f? Okay, there's a sign change right here, right? Negatives to positives. I'm assuming that it's all negative before, all positive after. That's dangerous as we go on, but for right now we're assuming. Why did it change from negative to positive?
Changes directions.
Yeah, it kind of changes behavior because, guys, from negative infinity to 0, you already said it. What's my graph doing? Decreasing. And what signifies decreasing in a first derivative? A negative slope, because it's saying, oh, hey, look, he's going down. What signifies increasing? I'm sure we've kind of mentioned a couple of these things, but it's been offhand and it hasn't really been on topic. So right here, chapter 5, analyzing function behavior. If you have a negative derivative, my function will be decreasing there. And if you have a positive derivative, it'll be increasing there. Why is 0 left out of my increasing, decreasing? Slope is 0, so my rate is 0, so therefore I am momentarily not doing either. I am stopped, right? If I'm thinking about rates. How can I see a second derivative in my original function? We'll talk about that question in a second. We've already said, oh, second derivative means he's a constant rate, but we can actually see a second derivative, or at least the idea of him, in this graph as well. But first of all, let's talk about him. All right, guys, what do you look like? A loop-de-loop? A whoop-de-whoop? He looks a lot like a cubic, right? But kind of stretched out and shifted a little bit down? Those are the words you could have used. Okay, so, silly goofs. He goes a little down, right? And it's 4 times, so he's been stretched. And he's a quintic. Oh, that's exciting. With n behaviors of, remember last year, odd function, positive odd function, n behavior to the right, he's increasing to the left, he's, remember our dance moves? No?
No.
Come back. So that's what I do. That's it. Okay. What's going on at 0? Is there anything special there? Like, is it just like a
Inflection.
inflection? What? Inflection point?
Right?
How do you know he's an inflection point?
I'm taking a guess.
How is an inflection point defined?
0.
Yeah, but that's not the definition because his slope is 0 too. How is an inflection point defined? He does this. What's that mean? It hits a point
And then keeps going.
and then it keeps going. But couldn't you like hit a point and keep going that way?
It slows down.
Kimmy, hang in there, bud. Inflection point. What's going on at an inflection point? You
Slowing
see it.
down, it's stopping.
Oh, come on. Greek algebra 2. What's the definition of an inflection point?
Increase.
A point at which the function changes,
Direction.
Sign.
Slow.
not direction, because, hold on, let's talk about this for a second. Is he changing direction? Oh dear, I can't move it. Is he changing direction at, oh, there we go. How do you move it?
We'll just pretend.
There we go. Question, what direction is he going in?
Positive direction. To the right.
So what's he doing always and never not doing?
To going to the right.
He's increasing from left to right, guys? And he's only increasing, so the point of inflection does not change the direction, right? Because he's increasing, he's going to keep on increasing. He kind of like slows down for a bit, actually he stops for a bit, and then he keeps going, but he's still only increasing. We could technically say like negative infinity to 0 and 0 to infinity. Probably we should have a u in between, whatever. Not changing direction. What's my first derivative? Let's start talking about him for a second, see if we can figure it out.
X to the fourth.
F prime equals 20x to the fourth, that's it?
Yeah.
What would his graph look like? He's even. What's my end behaviors? Right?
He's gonna have a bump.
Does he have a weird bumpy bump in the middle?
Yeah.
How do I know that?
I don't know.
There's no other stuff taking away from him, like cubic ones or squared ones or linear ones or constant ones taking away from him. He's just going to be a parabola that's really, 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 really...
Bit flat. Fat.
Stretchy. Yeah. Close together.
How do I know he's really, 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 really steep?
Because it's a vertical stretch.
This is modeling the numbers of my slopes, right? So, question. How quickly does he get really, really high positive? Really quickly. How quickly does he get really, really positive again? Fast, okay. How do I know a point of inflection on a derivative graph? Well, something's changing here too, right? Here, my function kept on increasing. No big dealio. But what did my derivative start doing at 0? Changing from decreasing to increasing. So maybe a point of inflection can be defined by I'm slowing down and then I start speeding up. Interesting. Let's do one more. What's my second derivative?
8x cubed x cubed.
Which looks like another, but centered at 0, 0, and really, really steep again. Actually, way more steep than he is, but that's the best I can do. You guys went ahead and plugged in values, right? Plugging in -2, what'd you get? Negative.
320.
Sorry, I'm in the first derivative, not negative. Positive 320, and then -1 was 20, then symmetric, right? Around 0. How about my second derivative? Plug in -2. Negative for -1. So a point of inflection doesn't make the behavior of f change necessarily, but it does change how the rates are changing. And it's a 0 of my second derivative. My signs of my second derivative didn't change at all here. And remember, we're looking at, once again, the graph of my original function. Of course, I'm asking you tons of different questions, but we're looking at the graph of f, thinking about the signs and sign changes of the first and second derivative. We figured out, go back, we figured out then, or before that, the sign of the first derivative tells me whether the original is increasing or decreasing. That's a characteristic of f that the first derivative tells me, the signs of the first derivative. And actually a sign change of the first derivative is going to tell me about minimums and maximums. Interesting. But what is the second derivative telling me about f? My hint was the point of inflection. Something is changing at that point of inflection that wasn't changing at this minimum. Jose? Yeah.
Why is this first derivative below the original?
Oh, good question. He shouldn't be, because he wasn't translated down. He would be right there. Thanks, Jose. Good call. Nobody can remember the actual definition of a point of inflection?
No.
A point of inflection, you didn't remember last year either, is the point at which concavity changes. Question, what concavity did this function have for any x?
Concave up.
Positive, concave up. Positive, hey, they're all positive, concave up. Question, what concavity did my function have up until the point of inflection? Concave
Down.
down. How'd you know? Because it was a frown, right? And it's negative concave down. Interesting. What concavity does he have after? Concave up, like a cup. And he's positive. A point of inflection is a point at which concavity changes. You basically just got the intro to the entire chapter. If we can figure out how all those work and how to apply them, then we will be ready for our next test, but we're not there yet. Here we go. Increasing, decreasing. There are lots of words. We don't actually need to write any of them. There's a graph that I'm going to kind of summarize everything on. Okay, there's a graph I'm going to kind of summarize everything on. You don't necessarily need to write all these words. So let me zoom in and take what we just did.
Do we have to write some of it? Can I not write any of it?
That's always an option.
Graph is super important, and let me highlight a few things that are as well. First of all, we need to remember that, and we talked about it, but we haven't written it down, that we are always going from left to right. Right? We're always going from left to right. It's technically pre-cal review, so most of you shouldn't really need to write, hey, it's increasing if it's rising, and it's decreasing if it's falling. That's the easy part. But what we're adding to it, remember, increasing as x's increase, the y's are increasing, decreasing as x's increase, y's are decreasing. So let me skip down to what you need. As we go from left to right, we can look at graphs and figure out how they're increasing, decreasing, increasing, but that's pre-cal. So why are we talking about it now? Because we are going to be able to make these judgment calls? I don't know. That's a bad way of putting it. Make these deductions about how an original function is increasing or decreasing from the signs of the derivative. Meaning, without even needing to know f of x's graph, we can look at the sign, oh my goodness, the sign of the derivative and say, hey, if he's positive, I know my function is going up. I might not know what it looks like, but from the derivative, I can tell where the original function is increasing and where the original function is decreasing. And of course, we've already talked about this, but it's never bad, I should say, never bad to remind ourselves. We can also tell ourselves where our original function is constant. And that's basically, guys, what the entire second paragraph says. Increasing, decreasing concept can be associated with the slopes of the tangent lines. If the slope is positive, then my function is increasing. If the slope is negative, my function is decreasing. If my slope is 0, my function is, in essence, if you're thinking about rates, momentarily stopped. So there we go. That's the important stuff. The rest of the words will be there if you guys want to look at it, but the graph is the important thing. With that,
Just do it. Just do it.
so guys, I could keep asking you the further questions, but I did want to separate increasing, decreasing from concave up, concave down, even though we did do like a huge preview of everything. So guys, where would you say, on what intervals, reviewing pre-cal basically, is this function increasing?
On 4 through 6.
4 through 6, not 4 to 5, 5 to 6, because isn't it still increasing at 5?
Right.
How do I know? Because what's the slope?
Odds.
Okay. So it's increasing everywhere from, wait a minute, closed, open, what do I do?
Closed. Closed.
Closed.
Bracket 4.
Oh, it is at the point.
6 bracket.
There could be some debates as to what, but guys, what's actually occurring at 4 and at 6? It's momentarily stopped. So therefore, it's open. 4 to 6. Alright, decreasing. Well, it's going to be everywhere else. So how do I know? Because the slopes are down, 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 down. Okay, so from 1 to 4, right? Why am I using a U? It's or. Why isn't it and?
Because
What's and mean in math?
both have the same.
Remember inequalities when you had the sandwiches and you had like, okay, it's greater than this and less than this, and at the same time overlapping?
yeah.
What's or? Separate intervals. What do I have?
Separate.
Got it. Moving on. What? Whoa! Where's my graph?
Where's the
Draw
draw?
it.
Don't tell me.
Can we do this without a graph?
No.
Yes, ready? How? Not with the function, but with his, because the slopes of the derivative, the signs, tell me about the behavior of the original. So therefore, f prime of x is equal to,
3x squared.
Minus 4.
That's right.
how can I figure out where he's negative and positive? Just start plugging in random numbers and hope I'm right?
Make a table.
First,
I could maybe graph him. Do you want to do that?
I want.
Yeah, I'd rather graph.
Would he be easier than the original one to graph?
Yeah.
What would he be?
Down 4.
Down 4.
A bigger.
What would his zeros be?
Oh.
Plus 4 divided by 3 square rooted.
No way, dude.
No.
Yay.
Around
Right? Plus 4 divided by 3 square rooted, so plus or minus 2 over root 3. That's ironic. I don't think it was on purpose. Negative, sorry, unit circle. Never mind.
How do you do that?
I said it equal to 0 and I solved. How does that help me? I want to figure out where the original function is increasing or decreasing. How does the graph of the derivative help? What are the... Oh, we're bringing something back.
number line.
There were different ways of doing it last year. This is my way of doing it. If I was trying to think about the signs of f prime, if I want to think about signs of a function, I use a sign chart.
Okay.
2 head nods. Last year sign charts? Nobody? Anybody?
Yeah.
We did this. You guys did tables. Either way, same dealio. Signs of. Guys, why am I stopping? Why am I using the zeros of the function to separate? It's called IVT, intermediate value theorem. It's called I can only change from positives to negatives at zeros. So I find the zeros of my function. That would be step 1. Then I say, what are the signs before this 0?
Negative. Positive.
Don't look at the slope. He already is a slope. Look at his sign. What
Positive.
y value does he have? A positive. What is he in between? A negative. What is he after?
I remember.
A positive. So what's my, wait a minute, if the slopes are positive, don't look at his graph. He's just telling me about slopes. If the slopes are positive, what is f doing?
Good to go up. Increase.
F's behavior. F is increasing, decreasing, increasing. Oh my goodness, he's going to have a W. Not a W. What would that be?
Wumbo.
A Humpty Dump. A Humpty Dump. I
A
don't know.
wumbo.
Yay.
And this is how, guys, at the end of this chapter, one part of this test is going to be a really, maybe not really, a pretty nasty function that you would never have been able to graph before. And I say use derivatives, second derivatives, pre-cal, all of the above to get me an exact graph of who goes. We have 14 things to go through. We're just starting on the process. So enjoy. We're just doing increasing, decreasing. Homework is split up into different
Parts.
Is it different parts? Hold on. We're going to tear apart more about increasing and decreasing tomorrow. Aha! My hint for homework number 21, which you are supposed to start tonight, which will be due on Thursday, is you will not know all the characteristics about it, and guys, I'm betting he'll be due Friday, just a heads up. But you do know how to find derivatives, and any function you're asked to analyze, you do have to find its derivatives in somewhere nasty.
STEM club today.
So if you want to start on homework, go find derivatives on a separate piece of paper, and then we'll use them as we do homework tomorrow. Bye, guys. We do have a STEM club today. Not really sure what we're talking about.